Alright, let's check now the aerodynamics of the body and the nose cone. So, as I told you before, the body and the nose cone are trying to destabilize the rocket when it is at a certain angle of attack. They're going to fight against the fins, and at one point they're going to win. And that's why, well, rockets they have a certain limit angle of attack for flight conditions and rocket geometry, in which the body and the nose cone will win the fight against the fins and are going to destabilize the rocket. If not, well, this is intuitive, because if not, well, you could spin the rocket and it could be flying at 90 degrees. It could be, if this is a rocket, it could be flying at an angle of attack of 90 degrees, and yeah, you don't have restoring moment when it's like this. So the equations pretty, yeah, they're intuitive in this sense. So the Cn of the body is equal to the absolute value of sine 2 alpha times the cosine of alpha over 2 plus 1.3. Let's put capital L. I'm going to use capital L for the total length of the rocket and capital D for the diameter of the rocket. And then sine squared of alpha. Oh, sorry. Oh, not again. Don't know why it's extremely buggy when I try to move it, but hopefully, yeah, gotta learn how this works. And now I'll line a bit. Never mind. We're gonna see the plot of this in a moment. Well, first I'm gonna tell you the formula of the position of the aerodynamic center of the body plus nose cone, which is this: the length of the nose cone times 0.63. This factor here, sorry, I always forget to get this off for the videos. Okay, this factor over here, this is what Fleeman suggests, but it could slightly change. It doesn't really, sorry. It doesn't matter too much, but just to let you know that this could slightly change in function of the type of nose cone you have. So it's not going to be the same if you have a conical nose cone than if you have hack series. I think it's spelled that way. Hack series nose cone, or jive, or you know, tangent parabolic. I think those are the typical kinds. But still, it's a small variation. We're just gonna keep the 0.63, but just to let you know this small thing. So I haven't finished yet. And then we have 0.05 of the length times sine square alpha. All right. So let's see. You can play around with these to see and plot them. I've done it for you. I've done the CN of the body. You can do it with the position of the aerodynamic center. We're going to check that. All right. I just plotted you the function of the cn, function of the angle of attack. So as you can see, it's kind of parabolic, not quite, but this is a trigonometric function, but it's kind of parabolic. It's not linear. It's definitely not linear as the fins. So maybe we could approximate a linear just in the first angles of attack, maybe up to 5. So up to then, it's going to grow quite a bit. So at some point, oh sorry, this is not. I told you this is 5 degrees. No, this is radians. So at some point, we're gonna have that the moment due to the body and the nose cone are gonna win. Let's say that there's gonna be some point in which the moment of the body are gonna be equal to the moment of the fins in a certain alpha. Okay. Let's call it alpha limit. And this alpha limit, if you can check that if these two moments are equal, well, the distance between the aerodynamic center and the center of gravity has to be 0, because we still have to be at the same point of the whole rocket I'm talking about. So we still have the normal due to the body, and we still have the normal due to the fins. So the only way that we can have no moment on the overall rocket is because the aerodynamic center is on top of the center of gravity. At this point, the rocket is going to be unstable. If this alpha limit is really high, say you put ginormous fins and maybe you get alpha limit, I don't know, 25 degrees. I still wouldn't believe that, because planar fins are gonna stall probably before that. So take it with a pinch, of salt, because it could be unstable way before this alpha limit. Okay.